by defining poles. Any ideas? I mean, frequency is one. I mean, bandwidth change, yeah. What else? Essentially, all transient response we can describe. Right? Everything you decide that pole is underdamped, overdamped, rise time, summer time, all these things. You're describing how I want the response to be. This is perfectly great. Right? Guarantee we're stable, which is good. Put all our poles about that way. For the observers, we can always make sure that observers are faster than our controller. Why do we want that?
So you get sampling errors?
Yeah, any kind of delay we have, as you see in the thing, slows the system down. So we want to make sure we can estimate what those states are as quickly as possible. Right? And remember, why do we make observers?
If we can't directly measure.
Maybe we can't directly measure a state, right? Or, what's the other reason? Maybe we can't measure them all, but still make an observer.
Just in case the measurement device isn't very accurate.
Not very accurate due to noise, things like this, and accuracy. So, several reasons. Now, there's a whole other approach to this. Right? Instead of defining where my poles are going to be, I'm going to put limitations on our states and inputs. Right? Basically, we call it performance index. Example of these things, especially makes sense for regulator. I want to keep the position within a certain range all the time, no matter what disturbance I might get. Practical example that might be, take cruise control car. I want 65 miles an hour. I want to keep it that way. Don't want it to vary very much from that. Right? The autopilot airplane, I want to keep a certain speed, I want to keep a certain altitude. How much variation am I going to allow for that altitude? So, how am I defining poles for such things? I'm not. I'm defining, I want to minimize or maximize something, typically minimize. We're going to be minimizing states, or minimizing changes of states. So that's one example. Another example may not be obvious. Maybe I want to design a, which I wish they would do this with cruise control, minimize energy, minimize your gas mileage, right? Maximize your gas mileage. So minimize such things as energy. How could you do that? Well, maybe by defining some states. States that define energy around what? Like kinetic energy.
So you're
That's what is M, velocity. Right? So I might want to minimize the velocity. Okay. What else could be minimizing energy? Well, I have something driving the system. Right? I have what are state equations. Maybe I want to minimize U. How hard it tries. Right? What poles do I have to have? No, I'm not defining poles. Defining minimization. One last one is often looked at is not really a state. We won't be able to do it very easily here, but minimize time. That comes into an interesting set of controllers, which are basically what we call bang-bang controllers. This is the race car problem. I'm trying to minimize time. What's the race car driver doing? Well, what's the gas? The accelerator. state. Full on. What's the break? Full on. We need it. Right? This is Saturday night on State Street. Right? Or actually here from red light to red light. Right? Certainly is not minimizing energy, but we will minimize some. So all these things we're in. So all of these are essentially path penalties. That's penalizing states, energy, whatever, over the time it's running. We can also minimize endpoints. We usually don't worry about the beginning point. Why?
Because you have no control over it, or?
We know where we are.
Yeah.
Sure, yeah. Mostly endpoint. Example of that, maybe the airplane problem again, is, I want to find I'm Delta Airlines, I want to minimize energy in my flights, save me gas, saves me a lot of cost. In fact, we should minimize cost, you can see too. One of all these things, dollars, people have done that. So it could be minimizing energy, save gas, but that airplane better arrive at the right airport at the right time. And so there's a penalty on that. So being late, early, usually no penalty early, certainly penalize late. Penalizing missing the runway is a serious one. Read every once in a while someone lands at the Walton Airport. Computers somebody does that. You imagine this for spacecraft things. Get to the space station. I want to get there at accurate time, accurate place. Right? In fact, that's a good one when you're doing spacecraft flights, putting up satellites and things. What's being minimized? A lot of these.
Fuel consumption?
Yeah, energy. Right? If you look at the flight it takes to get out to Saturn flights to the far planets, I think the Pluto, I can't remember all the routes that thing went on. It went around, I think, Moon, Earth, Venus, Earth, Mars, whatever these things get flying around in the inner solar system for a while. Kind of building up energy until it's swung out to the far planets. And I think this is true of the one that went to the Galileo, and I think also the one to Saturn.
Is that Voyager?
Cassini. Yeah, just one of all those astronomers. Those boosters didn't have enough energy to get to this planet directly. So most of the space flight things are minimum energy because what's the costly thing here? Get the bloody things off the ground. A lot of fuel. In fact, the Saturn V, that was the one that went to Neil Armstrong and got it off to the moon. It did not have enough thrust to lift itself off initially. It actually burned off enough fuel while sitting there warming up the engines, lightened up enough so it could actually take off. The thrust was not equal up to the weight of the initial weight of the missile. I just figured this out, they did my hand too. Another movie, I like movies. I haven't seen it yet. It's what about the,
Hidden Figures?
yeah, what's it, what is it?
Hidden Figures?
Hidden Figures. About the women, black women, who actually did the calculations for NASA for all the air flights and their things. Because they didn't trust, they didn't have computers. They have electronic computers. So they had all done by hand. Pretty fascinating. Okay, so, got the idea of what we want to do. The question is, how do we do this? Right? I want to minimize the conformance measure. So I need to define a conformance measure. And I want to define it, see different symbols for this. I think later in the notes I use V, so I use V here. Typically, have two parts. So input penalty is just a penalty on the end. No calculations here. Pass method integrated. Some initial time and final time of, okay, here I'm using G, I'll change that later. Of all my states, my inputs, and time. So this is what we call the path penalty. J, or V here, is a scalar. Right? So all the states, all these things, inputs are in vectors, but I'm writing in a way that end up with a single number that I'm trying to minimize. How do I minimize and maximize?
The derivative?
It's derivative, right? With respect to what?
Time.
In this case, it's time. Little tricky here. Oh, it's vectors and everything. In fact, I may not know what the function is. Right. I'm not going to get into the areas of variation calculus. But if I have a function, you know how to find the minimum maximum, right? Find the derivative with respect to the variable times 12 equals 0. Look at the second derivative, see if it's the maximum minimum. Higher level that way. I don't have a function. Right? I want to find a function that minimizes something. How do you do that? Well, that's what's called calculus of variations. And it finds functions to minimize. It's really what we're going to be doing here. So we're not going to do it with variational calculus methods. We have a class in that. Math class has classes in it too. Optimal controls, we go through half the class is really variational calculus problems. Really kind of fun things. And if we talk about regulators for system, what about the endpoint? Regulator, basically, I'm going to be writing this out to infinity. What's T final? Infinity, right? So for a regulator, I don't need to worry about this thing. Right? Won't worry about the endpoints in this class. We do that in the optimal controls class. Here we won't. Okay. Okay. So what we're going to do is a couple things. I wanted to be able to define a performance index, something I want my system to be doing, minimizing whatever states I want, input and everything. And then how do I figure out what gains I'm going to use to obtain that? Right? The final result is the same as what we've been doing. I have states. I feed those states back through some K, create U. All right? The only thing we're going to do is a new way of calculating this case. I'm not going to do pole placement. I'm going to do, ends up being called a Riccati equation. So I've got the idea here. All right, so let's look at how to define some of these performance measures. What I want to do is basically define some G matrix or G function here to do this. And the most common way of doing this is to square the terms. also, of course, square y squared. When do we square things? One sign, all positive, because if we do a minimization of just number, what's the result of minus infinity? All right, we don't want that. Why else do we square? Why not use absolute value?
You want to get rid of the negative square values.
Well, squaring or absolute value will do that. Get rid of it.
Absolute value doesn't have a derivative at certain points.
Yeah, absolute value is discontinuous. I want to be able to do a derivative, because what we're going to be doing is derivatives. And I want to make sure I have a nice differentiable function, and squaring does that. So kind of mundane reason. You could do it, and there's people do this with absolute value. It's a little bit messier. Okay. Well, I have all these squares here, and x is really a vector. Stevens. It's a new tweet for Riverwood. X is a vector. Right? There's a nice way of writing all these things squares with vectors. I did this and that be kind of subtle for you. One of those whipping-off problems actually did this. Yeah.
Is it the x vector transpose times identity?
Yeah. Something like that. And I'll say some more matrix here. Right. Doesn't really need the 1/2 there because it's just a number scalar. So this really, if you think about this, is all these things squared. Say quadratic. So to define our performance measure, we now need only to define what? The R matrix. Set of coefficients. So R is a matrix of coefficients. They're basically weighting. States. How much do I care about controlling position? How much do I care about minimizing velocity? How much do minimizing voltage, whatever? Sometimes I don't even care. I get zeros for some of this. Right? Else I have this guy, U. I'm going to have that as a separate quadratic. You'll see when we derive this line. So again, U can be a vector. Both one, both one. And if I have these backwards in Q here, sorry. Q there, and R here. We would do that. Right. Again, the matrix of coefficients. How much do I weight the voltage to this motor? How much do I weight pressure on this pump, whatever we're doing? Okay. All right. So now I have our performance index, and I'm going to worry about the endpoints here.